I'm standing above Diablo Lake in the North Cascades in Washington, which you would be forgiven for thinking is the world's largest reservoir of blue Powerade. Sometimes it's blue, sometimes it's green, sometimes it's something in between, but it's not the only body of water in Washington that looks like this. In fact, the Earth is full of fantastical colored water like this. But why? I've been obsessed with this question for 2 years now, and what I've found is that the answer is many levels deep. So we're gonna start at the surface, and we're gonna keep on asking why, like an infant child, until it actually makes sense. That was the first answer that I got when I Googled this, but it didn't satisfy me. 2 questions. First of all, but why are there minerals in the water? And second, why do the minerals turn the water a bluish-greenish color? Well, the first question is a lot easier to answer than the second. It's glaciers. Washington is the most glaciated state in the US outside of Alaska, with over 700 identified glaciers in the North Cascades Mountains alone. But why do the glaciers produce minerally water? Glaciers grind away at the mountains that they sit on like sandpaper, producing a fine rock flour. During the winter, this rock flour builds up beneath the snowpack, but then when the spring melt occurs, streams that emanate from the glaciers carry that rock flour into rivers and then lakes. There's too many glaciers that feed Diablo Lake for me to show you this clearly in action, but here at Blanca Lake, there's just one source, the Columbia Glacier, up there. So I'm gonna journey out to it and show you. I think I'm about to see it. Ooh, there it is. But why do glaciers grind mountains up? Well, what exactly is a glacier anyway, aside from an excuse to upcharge bottled water? Glaciers are basically bodies of ice, like this, that stick around all year. For reference, it's August. When you get enough snow in one area, the weight of the snow will compress and squeeze out all of the air from the ice at the bottom, creating what we call glacier ice. This is different than the ice in your freezer because this ice, its crystalline structure, is literally incapable of supporting its own weight. And so it flows downhill like a fluid. And as it flows over terrain, the brittle top part goes creating crevasses like these. It's common to refer to glaciers as rivers of ice, and in places on Earth where they're still big enough to occupy entire valleys, they really do look like rivers. They even flow like rivers, being fastest in the center and slowest on the sides. But you're probably wondering how fast they actually move. Now, it hugely depends, but the fastest glacier movement ever recorded was 98 feet in a day in Greenland, whereas a more typical, slower glacier probably moves 20 inches in a year. When you're sitting beside one like I am, you can actually hear it groaning and creaking and cracking, and to be perfectly honest, it's kind of scary. God, that's creepy. The sound artist Jacob Kierkegaard recorded dramatic examples of this in Greenland in his project entitled Melt. So to oversimplify things a bit, it's that movement of the ice downhill that scrapes and carves and grinds the mountains into the rock flour. And you can see the scrape marks, they're around here. I'll show you some. So there's some of those scrape marks that I mentioned. Rocks and stuff on the bottom of the glacier scraped those into existence back when it was a whole lot bigger than this, flowing downhill. In fact, back when it was bigger, it excavated this entire thing into existence. Okay, so we know where the minerals are coming from, but why are they making the water bluish-greenish? If you're like me, you're probably thinking that the minerals themselves are bluish-greenish. And you might even be thinking, maybe I can figure out what minerals are in the water based on its color. As it turns out, you can't, because the color doesn't come from the kind of mineral at all. It doesn't even come from the color of the individual rock particles. It comes from the size of the rock particles. If that sounds crazy to you, that's because it is crazy. Particles of certain sizes, pretty much regardless of what they're made of, do a physics trick with light called scattering. So again, if you're like me, you're probably thinking, okay, wait, so you're telling me that if I were to take some gray powder made of particles of just the right size, put it in water, the water would turn blue? Yeah, right. And yeah, that's actually right. And you can do it. The easiest way to demonstrate this is with milk. Now, I know that seems pretty incomparable to rock flour, but hear me out. All milk is tiny globules of fat suspended in water. And those fat globules are actually the same size as many of the particles of rock flour that scatter blue wavelengths of light. All we have to do is heavily dilute the milk so that the colors that we're seeing are coming from the light scattering as opposed to the white color of the fat globules. So if you want to follow along at home, you just need a cup of tap water and a cup of dairy milk. Pour a tiny drop of this milk into the water, mix it up, and watch it turn blue. This is best observed in a dark room with a flashlight, but it works anywhere. And if it just turns cloudy white, you've added too much milk and you'll need to dilute it with more water. But what is this physics witchcraft behind light scattering? But why, and I know this is getting annoying now, do particles of certain sizes scatter certain wavelengths of light? I want to start this off with a disclaimer though. I do not have the background in physics to speak on this with authority. I spent about 3 weeks reading primary source articles and then physics stack exchange answers until I felt like I understood this at a deep enough level that I could make a simplified explanation of it for this video. I also had invaluable help from an old physics professor of mine, but optics is not her specialty either. So if anybody watching this understands this stuff better than I do and notices a mistake that I've made, please do correct me in the comments. My goal is to give you a feeling for how this effect happens, but not to teach a physics class. To give you an idea of why scattering is weird, we need a real basic understanding of why things usually have color. So to set this up, we need to establish that light is a wave, and that the color of light is determined by its wave length. Blue light has a shorter wavelength and red light has a longer wavelength, with green and stuff in the middle. Yes, violet is even shorter than blue, but we're ignoring that for now. White-ish light from the sun, or a typical light bulb, contains all the visible wavelengths of light. That's why it looks white. For something to have a color, that white-ish light hits it, some wavelengths or colors are absorbed, and then some are reflected back to our eye. Most of you are probably familiar with this concept, and it's why this shirt here is red. But here's where I'm going to challenge your fundamental intuitions around color. What if I cut this shirt in half? Will it still be red? Okay, yeah. But could I cut it in half so many times that it loses its color or changes color? Well, the answer is yes. If I were to cut this so small that it was just a few microns across, that's about the ballpark size of common dust, it would absolutely lose its color. You've never seen bright red dust hanging in the air, have you? And that's because airborne dust is pretty much always the color of whatever light is illuminating it. So why is that? Well, dust is just too small for that absorption-reflection regime that we're used to thinking about. Instead, light scatters off of dust. Scattering means that instead of passing through the material, instead of absorbing into the material, and instead of reflecting off of the material at some specific angle, the light kind of hits it and explodes in all directions, more or less. I actually have a video that shows this really well. I found it on this teeny tiny YouTube channel called Ripple Tank Demos. Yes, these are water waves and not light waves, but the wave dynamics are actually the same. What you're looking at here is a tank of water from above. That bar at the top there vibrates and creates waves in the water. The waves then hit that circular obstacle, which represents our dust particle, and you can see, instead of reflecting back like you might expect, the waves scatter out in all directions. You may have seen this before and not even known it, looking out at a dock in the water on like a lake, a river, or the ocean even, where waves are hitting the wooden pilings below and the water is kind of radiating out in all directions from the pilings. If you want to go even deeper into the physics here, the Science Asylum has a really good video showing what's happening at the particle level. Now, this isn't true if you've got just a pinch of dust in your hand, because a pinch of dust is interacting with the light as this big clump, not as these tiny particles. So they need separation. They need to be either airborne or, in the case of our rock flower particles, they need to be suspended in water. But dust isn't that blue color that we're trying to understand. It's usually white. So how do we get to blue from here? Could I make my shirt particles even smaller until they change color again? Unbelievably, yes. So what if I set the shirt on fire, turning it into tiny smoke particles? What I'm trying to show you is that smoke can be blue. Not all smoke is blue. Sometimes the particles are a little too large, and we're doing our best out here. I just wanted to set things on fire. I do have pictures. It'll make sense. Have you ever noticed that cigarette smoke has a blue tinge to it? Or maybe you've seen blue smoke coming off of a grill? I had a lot of exposure to blue smoke 2 years ago when I was driving through Oregon during the wildfires. What's happening here is that some smoke particles are so small that they disproportionately scatter more short wavelengths of light than the longer wavelengths of light. Now remember, blue light has a shorter wavelength, and so the smoke appears blue. There is some math that explains really well why this happens, but for me, I need an illustration. So I drew this out, and I think it's going to make sense when we look at it together. Okay, I have two waves, a long one, which is representing red light, and a short one, which is representing blue light. These are not proportionally accurate red and blue waves, and there's some definite problems with representing light spatially in this way, but everything in this illustration is exaggerated because I'm making a very specific point. So I drew a cloud of particles for them to travel through where the particles are really small, smaller than the wavelengths. Smoke particles are not quite that small, but again, I'm exaggerating. Then I highlighted each particle that the wave touches on its way through the cloud of particles. The more particles the wave touches, the more scattering happens, and you can see the blue wave, being shorter and more frequent, touches way more particles than the red one does. Now, here's a drawing where the particles are way bigger than the wavelengths. These are representing our dust particles. With these, you can see that the red wavelength is touching approximately the same number of particles as the blue one. What I'm showing here is that big particles won't scatter more blue than red. They scatter all the colors of light about the same. This is why dust particles appear white, because they're scattering all the colors the same amount, all colors together being white. But small particles like those in smoke, rock flour, and milk are small enough that the short wavelengths interact with them more than the long wavelengths do, making them appear blue. This will help you see that milk demo in a new light. That suspension of milk fat particles in water is like an obstacle course for the light, and it's disproportionately obstructing and therefore scattering the short blue wavelengths. So check this out. I'm shining my white light through the glass before stirring in the milk, and you can see it's coming out white on the other side. But watch, I stir it with my finger, creating that obstacle course and scattering out the blue light instead of letting it continue on in a straight path. And look at that. The light coming out the other side looks almost orange now, because what's happening is the milk particles are scattering out the blue. It's like it's stripping the blue out of the white light. White light minus blue light is red light.
So why is Diablo Lake blue? So why are trailers so loud? Why are there two of them? So why is Diablo Lake blue? Well, glaciers grind up mountains into tiny particles which are transported via streams to this lake, and then when they're sitting there, through the magic of physics, they scatter just the wavelengths of light that our eyes perceive as blue. Or green. Or blue-green? Why are they sometimes blue, sometimes green, and something in between? It's not algae or anything living like that, so get that out of your head right now. The last word on this came from a 1980s Norwegian paper where they studied this exact scattering phenomenon. What they measured was that the most scattered wavelengths for the rock flower particles were in the edge of the blue to the edge of the greens. Now maybe this comes from the fact that the rock flower particles are jagged and irregular. They're not perfect spheres, which is what all these models are based on. What I can tell you for sure is that these lakes and rivers tend to be their greenest during the springtime, and I see them get bluer and bluer as the summer goes on. So my pet theory is that the larger particles scatter more green and the smaller particles scatter more blue. So then as the summer progresses and the larger particles settle at the bottom, that accounts for the color change. By the way, it's not just Diablo Lake, my low-key undrinkable milk solution, and smoke particles that get their color this way. This same scattering mechanism is the reason the sky is blue, why my eyes are blue, why this absinthe and some agates are blue. I've seen this kind of blue being described as an illusion or not a real color, but I don't like thinking about it that way. I think as far as my human perception is concerned, all colors are real, but not all colors are the same. I think there's a good reason why Diablo Lake is so captivating. It's because the color coming from it is coming from a much rarer mechanism than the kind of colors that I experience in my day-to-day life. And knowing that makes the experience of looking at it even more aesthetically fulfilling for me. I hope it does the same for you, and thanks for watching.